Oh, thank you.
Hello, everybody. We'll wait a few minutes for people to join. That's not good. All right, hang on a minute here. Okay, I've just pasted a copy of the agenda into the notes file.
Hey, David, I don't remember. Is it difficult as a participant to upload the slides so that I don't do screen share? I only did it so far.
I don't remember. Janos is on. Janos, how should we handle this?
So it's you can upload as usual using the upload tool, and I can approve it.
Okay,
if I see it.
Yeah.
But I'm in the material page, so.
Yeah, I'm just looking. No,
So then, what I see here, there is this. But I see the chart view. There is an upload slides button here. This is the meeting we are at.
Oh, okay, sure. The standard.
I guess there is the. I
Oh,
hope
there,
you.
yeah. I thought it was in the Meet Echo tool, but it's on the wiki.
No,
on our.
No, it's usual data tracker. I think you go and propose slides there, and then Janos or I approve them.
Yep.
And thanks for doing this. We still don't have a sanitized version of Shusong's slides from the last meeting. Need to go reminder.
I see you have uploaded it. Let me take a very quick look before moving. Just a sec. Why is this? You still have the Chinese table?
Yeah, and that we are making progress on that. We've got the English translation now, but I didn't get around to it for this
no
time.
problem. I'm moving it, clicking on it. It looks good to me. There we are.
That is just the motivational section.
I don't bother too much with the title, if you don't mind.
Yeah.
And just so it's approved, and now I don't know how long it takes for Mitaco to.
It's fine. We have a topic number 1 first, so should be there.
I mean, we see it in the where do we see it in the Mitaco?
I don't see it as the slides yet, so but hopefully soon.
Meeting materials, no slides available. Refresh. Oh, it's there. There is a. At least the link is there now. It should be.
Okay. All right, now.
So the link is. Okay.
I'm sorry. Go ahead, Janos. I'm just going to go get the. There it is. We need to put this up to get started. So this is the Note Well slide. This is an IETF meeting. You're expected to be familiar with this because the provisions of this slide apply to all participants. Okay. Let's see, that'll take care of that. Now, all righty, here's the agenda. this should look familiar. I just basically I just keep editing this file every week to hopefully get the time slots right going forward, and insert the draft that we're going to do in item 2. We have a couple more drafts queued up for the next 2 meetings. We have Shafu's time slot draft, and then Antoine's new draft are tentatively queued up for the next 2 meetings. If people want more drafts in the queue, just send an email, and maybe I'll start maintaining the queue in the wiki somewhere. Okay, this is the agenda. Anybody want to bash it? All right. Consider the agenda bashed. Let's see if I just kill that. Bingo. Okay. That was the right thing for me to echo to do. So I guess we are on the sort of general discussion portion. Peng, I see a new version of the requirements draft was posted. Do you and the authors believe that draft is stable now?
Hello? Yeah, okay.
Yes, yes, we can hear you. Go ahead.
Yes, as some of the authors proposed some new requirements, and we add them to the new version, and but we just add one new requirement, and for others we add them as a text in the existing requirements. And for this version, we think maybe it's really better than the previous one, and also than the 0.0 version of the WGS draft. So maybe well, I think it is stable now.
Okay,
But I sent the updated version 2 weeks ago to the mailing list, and haven't got any comments on it.
Yeah, I apologize. So I hadn't found the time to do a full run. And I think with the slides today, there are a couple of discussion slides on the operational requirements, and I wanted to make sure if or how best they're captured in the requirements document.
All right, we'll have to see what happens when we get there. We do need to see a requirements draft because I think we've gotten to the point where we ought to at least be attempting to evaluate one or more of the existing TSN mechanisms. I view this as sort of test running with the requirements so we can shake out bugs or unanticipated problems with them without them reflecting on a proposed new mechanism. Let me quickly share. I did run a diff on that this morning just for my own grins. Let me quickly share. Let's see if I do this right. Dun, da, 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 da. That one, I think. Yeah, there it is. Okay, I popped this up simply to show. Here's 3.7, which is here. This is the new requirement that Peng was referring to.
Yes.
And you can also see the other major text addition just above it on the screen. So this is just for everybody's information, and I guess we'll come back to this during the item 2 presentation. Okay. All right. MeetEcho seemed to have survived closing that. That worked. All right.
Yeah, so for example, on that complex topology, I very much liked from one of the prior presentation, the explanation about the burst buildup in rings, right? So I mean that might be a good reference to add to that section to give some better understanding how to assess the requirement, right? Because I think that's one of our next issues. We can write requirements, but how do we assess them? And so those aspects are then they're very helpful, I think.
All right. So I think we're looking for a volunteer. We sort of had this discussion last time. I think we're looking for a volunteer or two or three to take the existing TSN mechanisms and attempt to evaluate them against the requirements. We know that they're not going to meet most of them, but having an initial attempt to do the evaluation will give us some confidence that the requirements are tractable before we start going through the new proposals. So looking for volunteers. Don't have to speak up now, but I think this is an important next step to make progress.
I just have a little bit of backlog on my on the things I wanted to do for DETNET. So in 2 weeks time or so, I can't do it something in the next 2 weeks, but afterwards I should be able to.
Yeah, and there are enough people interested in CQF. I mean, we have at least three drafts that are proposing to in effect extend CQF with a cycle ID mechanism. So between the authors of those drafts, I would hope there'd be at least one author who'd be willing to take take an initial attempt at evaluating the original CQF mechanism against our requirements. I think what we're probably looking for is about a sentence per section of the requirements draft saying whether it meets or does not meet and why it does not. We don't need a whole new draft on this. I would hope about a sentence per requirement would get the job done.
Certainly good point. If we can't get an answer from the folks now, I'll certainly take it up with them offline.
Yeah. I need to take some notes here. It would help if somebody else could get into HedgeDoc and start taking notes. I'm not trying to run the meeting and do all the note taking myself. Okay, I'm caught up again. So we're still in item 1, process-oriented topics. Any other comments, requests, questions? Okay, Turles, had you volunteered yourself as the designated victim to do the presentation on TCQF?
And, I think the colleagues are online, so they can jump in if I'm missing things.
Okay, sounds good. Why don't we do that? 'Cause I think you said you had some slides in there that may affect the requirements. So why don't we go ahead and go to item 2, do that presentation, and then we can return to requirements discussion and talk about next steps as we go along. All right. Now let's see if the theory works. I click on meeting materials, and I hit refresh, and I see slides.
Wow, I don't see slides. That's good.
There's a refresh button in the meeting materials window. If you hit that, Meet.echo goes back and looks. Okay.
Oh, you're right.
All right. So okay now. Yeah, and what's the right thing to do for me? If I click on the slides, I get a Chrome tab that I can share, but I think we want to do something different there.
Yeah, if next to the raise hand there is share preloaded slides, but nothing appears there for me. So I think just
Yeah, if you
wait a minute,
approve
wait a minute.
me, I
Share
can share the
preloaded
slides myself, I
slides.
think. Mhm.
Hang on.
sorry, Torres, what did you suggest?
I'm saying if David approves me, then I think I can share and run the slides myself. Otherwise, I always have to ask back and forward.
All right. I just hit the green check mark. So Turtles, let's see if this works.
This doesn't look that way. It says no slides available. Okay. Okay, at least for me, it's in the middle of the night, so I have some excuses why the tools don't like me now. Let's see, slides. No. If I click on the slides, just ask to share slides.
All right, let's go ahead and approve you again.
No, it still says no slides available. I don't know.
All right, I have the slides in a Chrome tab. So what I'm going to do is I'm going to go ahead and share that, and you're going to tell me to advance slides, and hopefully we won't get we won't have problems with queuing and forwarding of that request.
Yeah.
All right. Okay. So if I click on share preloaded slides, okay. So all right. So what we're going to have to do is we're going to do it the hard way.
Well, I can, yeah.
Okay, with luck, your title slide just showed up. And now if I go and fit one page and get rid of a few other windows, all right, is this reasonably visible to people on Meet.echo? Yeah, there it is. All right.
It's good. I think it's good.
Yeah, it's somewhat frustrating that we still can't figure out our own tool. So, all right, so here we are. Cyclic queuing and forwarding.
I'll even make it a little bit bigger. All right, go for it.
All right. So, and you can see on the bottom where the slides are. So this is presentation for what we've been talking about several times in the working group, hopefully with improved explanations and of course more time to ask questions. And as you see, there is now a lot of authors because we're in the process of merging two of the drafts presented already, and we're going to get into that. Next slide. So I was trying to figure out how to structure this this presentation, and as a completely opposite to how I've seen a lot of research work being done, where a lot of theoretical stuff is being done, and at the end some very insufficient explanation how this relates to reality and has actually been tested in reality. I wanted to try to start with the motivational stuff being not only the history of where we came from, but also what we have done over the years in support of it. And then the other points, I think we'll see them when we get to them. Next slide. Okay, next slide. So we've been on this since about 2018, 2017, when this was started to be looked into. And the first draft we presented was in 2018 until 2019 with Christina and a couple of other co-authors. That was also around the time when we had the Bangkok interim together with TSN, if folks remember that. Another draft in 2019 was also looking at MPLS encapsulation. And then, of course, because we didn't have the agreement and time in DETNET to work on this type of work, it kind of fell into disrepair and was revived when we were getting closer and finishing up on the charter items in DETNET. So 2021, a new version of the draft, queuing with multiple buffers was written. And then I started to work on with new co-authors coming from the MPLS side of DETNET to figure out how we can add to the draft not only the basic mechanism, but also the other pieces that hopefully are sufficient for standardization. And from that respect, it also focused then, as the name implied, on the MPLS encapsulation, because that was pretty much what we had a lot more complete in the DETNET forwarding plane than an IP forwarding plane. And with all the aspects of the IP forwarding plane being less well resolved, it seemed like a faster starting point. So then in 2022, when we discussed this in the DETNET working group meeting, David made the wonderful remark that we don't have necessarily the need for DSCP standardization, which would allow us a lot easier to do DSCP encapsulation in DETNET itself. And I changed the draft to be IP and MPLS encapsulation. And then Yizhu and other co-authors also added a draft that provided a lot more of the original text, improved on the explanation of the mechanism. That's what we're also going to review today in more detail. And so we're just in the process of merging these two drafts, and hopefully that should be also ready within a month or so, definitely before 117. Okay, next slide. So that's kind of the draft work on the IETF side. Within Huawei, what we call the whole thing is deterministic IP. So I think the name already implies that we're a lot more interested in IP and IPv6 forwarding planes, which is kind of I think easy to explain when you look at the landscape of service provider networks in China and in Asia, where MPLS just never had that much proliferation than the newer IPv6 technology. And so the two main vehicles that we used to validate the technology was, first of all, a very thorough, large-scale, high-speed simulation with, I think, NS3, if I remember correctly. So that was presented in IFIP 2021. That was already done much earlier, but took a while to get through to the conferencing side. So that is a very good mathematical review. I think for the model, the picture on the right-hand side shows a little bit the logical network that was tested for that. But to me, much more interesting, we also built a high-speed router implementation of the hardware. So that was based on off-the-shelf 100 gigabit Ethernet routers with an FPGA to do the cyclic queuing, just because that was not standard in that type of hardware. Now, of course, the cyclic queuing itself is very much standard on 1 gigabit and 10 gigabit switches that are built in the Ethernet space against TSN requirements. So those could much more easily support this technology than the high-speed switches. And that was also then validated with OMNET++ simulations on the larger topologies of AS1239, which is the well-known Sprint topology, with 315 routers and 1944 links. So both hardware simulation in detail and in large scale. Next slide.
One quick question on the slide I've
Yep.
just shown. Hang on, let me go back. On the lower right-hand diagram, The red flows or B is obviously best effort. What does the HP stand for in the green flows?
High precision. Sorry, that was another wonderful marketing term that was invented. So we could have said DETNET or DIP.
Okay.
CQF. Yep. Right. So the large-scale validation was done on the CINI research network across China. So that's similar to European American research networks, dark fiber connecting many of the cities, and then also having processes in place on how research work can be deployed there. So effectively, in different parts of the network, these prototype routers were deployed and then measured. And so the report, so we had problems with these web pages, so that's going to change. And those reports were just in Chinese. We have them now in English, so stay tuned. I'll send it to the mailing list once we have overhauled that. Next slide shows a little bit kind of eye candy from unfortunately still. Yeah, sorry, next slide. From that. So that's an example topology. I think the longest links that were used in this were several hundred miles long. So I think the total length, for example, just for the propagation latency, which of course is very important in the mechanism, was over 1,000 kilometers. And then of course also going across multiple hops, doing the injection of traffic, measuring the burstiness. Next slide. And then actually proving here that the latency really sticks within a very narrow window. So it's not only bounded, but it also has a very low jitter. Yeah, once the table is translated, it makes a lot more sense. Yeah, so this was just, for me, it's always good eye candy to know that there was a lot of validation, that this is not just a research project for which maybe at best a simulation has been done, but that this is a technology much further down the line, so that we feel very comfortable for saying this can be standardized in the IETF. Next slide.
Quick question. It looks like on the right, I see IP being compared to DIP. What is the heading on the two bold columns that seem to show the massive difference?
Yeah, so that I think is the total jitter, and so that's where on the IP that's best effort, right? And that of course shows that you have in the IP case across many hops. So the rows are the number of hops, and that shows then that you're accumulating more jitter in the best effort traffic, and of course you're not incurring more jitter in the deterministic in the CQF traffic.
Thank you, and I think we look forward to a version of this slide with suitable translation. Thank you.
Yeah. Oh, sorry, this is the Chinese class here. Sorry if you are on the wrong meeting. No, sorry, kidding. Next slide. Okay, so our claims, right? So TCQF can easily be implemented at scale in existing type of wide area network routers. TCQF has been validated through simulation, POC implementations in wide area network deployments up to 2,000 kilometer path. It provides very low latency, very low jitter, which we call on-time forwarding. And I think, and we're going to talk about that later in the slides, that's one of the core requirements for many core use cases. TCQF can support IETF network layer data planes. Validation was done with IPv6 headers. Draft currently supports IP, IPv6, MPLS, and then SR, SRv6, SR, MPLS are equally supportable. And of course, even my favorite topic of beer from the multicast side is also supportable. The header extensions there are another interesting aspect. And the biggest beauty would be that for immediate adoption, standardization of extension headers always being something that the IETF is slower with, where 6-man and MPLS working group would probably have a big say. We can do it without new extension headers for a good subset of the what the solution overall could offer with DSCP and traffic class. Next slide.
Let me quick interject on a little bit of structural question before you dive into the details. So my understanding from Shusong's presentation last week is that the basic extensions to the CQF forwarding, queuing and forwarding, are common between what you're doing here and what that draft was doing. And the primary difference is this draft is proposing just communicating a single identifier tag or cycle label, whatever term you want to use, whereas the CSQF draft last week is specific to something like SR or MPLS and is effectively communicating a stack of tags or labels to the same mechanism. Does that match your understanding?
Yes, that does. And unfortunately, I didn't have the time to watch the YouTube yet, so I'm not quite sure how much in detail she, for example, was trying to do a comparison in terms of complexities and or benefits downside between the two mechanisms. I could easily see that we merged that all together into a single solution. But obviously there are, pro and cons of the two options.
Okay,
and
let's
I think that's another discussion.
Cool. I was only trying to go after make sure we have a shared understanding of structure. I don't recall much in the way of comparison. It was a rather different architecture in that it relies on a centralized controller to make the label stacks work. Okay, thank you. Now we go to next slide.
Yep. Okay, so here is the wonderful joyride. Next slide. So, right, so we're starting with cyclic queuing and forwarding from TSN 802.1 QCH, as it was originally called, and then merged into the overall 802.1 standard. But if you hear QCH from TSN people, that means CQF. You can have never enough TLAs to name the same thing. And it was evolved actually as a very simple profile from the TSN time-aware shapers, which is 802.1 QBV. So the interesting part is that you don't necessarily in TSN equipment see that they're supporting CQF. You just need to look if they're supporting QBV, and then pretty much, it's a controller plane mechanism over there to configure that so as to do CQF. And so at the core of TAS and CQF are the per hop forwarding of packets based on their arrival time on each switch, right? So, this allows the, being built against the arrival time allows these two mechanisms to operate without additional new headers to carry, queuing information. And that was, I think, one of the big design goals. And so ultimately they were also designed against the requirements back then from TSN, which means primarily LAN deployments, intra-car, up to maybe manufacturing floor, and then speeds of 100 megabits and 1 gigabits. I think the maximum would be 10 gigabits in switches, but I haven't actually been able to validate which 10 gigabit switch interfaces would support it in the TSN space, but certainly be happy to hear about that from TSN people with respect to their knowledge. Next slide. So, and this slide was already shown in IETF, so a couple of repetitions here. So as you see, you have path here from left to right through 3 routers. Each router has 2 cycle buffers, and you periodically, let's say every 100 microseconds, are switching between these buffers. One buffer is receiving the packets, the other buffer is sending the packets. So it's kind of bucket passing, if you know that old scheme. So that obviously means that you very simply are having a well-defined per hop latency, which is the cycle time, and you are just having to fit all the traffic you want to forward into the cycle buffer. which you can calculate based on the cycle time and then the link speed. And so you're just periodically running this, and that way you get deterministic bounded latency and, of course, only cycle time latency. And on the right-hand side, the formulistic repetition of what I said. Now, the interesting part is that the propagation latency from one hop to the other is introducing a dreaded problem, which is called the dead time. And so we'll have that on a later slide in more detail. And that's the orange block. So I think let's go to the next slide. Should be the explanation of the dead time. No. Oh, no, we're getting to that later. Sorry. Oh, there is some. Okay. We've got a PDF issue, but hopefully we will survive. Now, the interesting part is that even though CQF was built for, in our opinions, rather low-speed networks, nothing against cars, it actually becomes a lot more attractive, fundamentally, the faster the networks become, right? Because the faster the network is, the more bytes you can fit into a buffer for the same length of time. And so the table below shows that, obviously, right? So whenever you increase the speed by a factor 10, you get 10 times more bytes in there. So you don't need to increase the cycle time to make more traffic work with this mechanism, but instead you can build very high-speed networks with very short latency incurred by the cycle time, right? On every hop, you need to wait a cycle time before you can forward the packet again. So that latency adds up. If you have many hops, that adds up more. But if you have 100 gigabit networks, you now got a much lower overall impact on that than in smaller networks. Slower networks, gigabit networks. Was there anything else? No, I think that's it. Next slide. So now here is that dead time issue, and hopefully that's visible. So this was directly taken from the draft. And so if you look here, what you'll see in the picture is that you have the buffer on cycle I-1 that is being sent, and on the upper part you see node A. So it is sending this this buffer content, just a sequence of all the packets, filling up the cycle, you know, let's say as good as possible. But there is propagation latency, there is processing delay. So there are a couple of aspects why these bytes arrive at the receiving node B somewhat later. And what we need to ensure is, because any byte, any packet being received can only be put in the right cycle buffer based on the arrival time, we need to make sure that the last byte of the last packet still arrives at the time before the cycle is being switched. So if the total latency that is introduced by the propagation of the link, by the processing, if that accumulates up to, let's say here in the picture, looks like 30% of the cycle time, that means you cannot really support the cycle to be full of data. You can only fill it up to 66%. 33% of the cycle you need to keep empty so that you can send out the cycle in time to arrive at the next hop. And so obviously the biggest issue that you have is that the speed of light is unfortunately still not changeable. And so when a network link becomes larger than, let's say, 2 kilometers, and for, I think was the cycle time, what did we calculate? Should have written it on the slide, something like 20 microsecond, then the dead time becomes larger than the cycle time and effectively have zero throughput. Now you can argue that you never need 100% of deterministic traffic in a network, so that's why some dead time may be acceptable, but it's certainly something that makes a design of a network, especially when it becomes larger, really, really problematic, and would be really good to avoid having to deal with the dead time and eliminate it. So we would rather like to have something that, independent of how large the network is, we can have 100% utilization. Next slide. So now when we go to 3-cycle operations, you see here, hopefully a little bit better visualization, although I'm not quite sure how well I get that into the draft then. So cycle 1, cycle 2, cycle 3, then cycle 1 again. So now we're cycling through 3 cycles, and we're looking at cycle 1, and it's being propagated to the receiver node B. And as we see, it does arrive somewhere in between cycle 1 and cycle 2. So what we obviously need to do now is to say, okay, packets from cycle 1, when they arrive, they need to be put into cycle 3, because obviously during the time that cycle 1 packets are arriving, we are sending out first packets from cycle 1 and then packets from cycle 2, right? So we need to kind of map anything from cycle 1 into cycle 3. So when cycle 3 is being sent out, we know cycle 1 packets never arrive. So far, so good. And we can even do this without, indicating the cycle identifier in the packet, purely relying on the reception clock, because we assume, or let's say if we assume, that the propagation latency is exactly accurate as it was in the TSN case, because, when a packet arrives exactly in this interval that we're showing here between cycle 1 and cycle 2, the controller would have had to figure out, okay, this is how high the propagation latency is. So in this period of time, all the packets that are arriving will be from cycle 1. So this can be done. This is also was proposed to TSN as the so-called multi-buffer CQF version. To the best of my understanding, that has not been adopted by TSN, but would certainly love to hear if that was adopted by TSN. So next slide. So now the reality, unfortunately, is that relying on the accurate arrival time is really impossible in large-scale networks. And that's where we come to the variations of the arrival time that we have to deal with in realistic, high-speed, wide-area networks, right? And the most important reasons for variations of the arrival time is the inaccuracy in synchronized clocks. And that is being measured by a factor called the maximum time interval error. And that pretty much means that if B thinks, some particular timestamp is time t, then the sender has thought it is time t minus MTIE up to the point t plus MTIE, right? So that is the window of difference between the timestamps in 2 synchronized clocks. And so CQF at 1 gigabit per second already requires sub-microsecond MTIE, so that the variations due to the MTIE do not impact the performance. So the MTIE becomes a factor in the dead time. You want the dead time maybe to be less than 10% of the cycle interval. You have other processing latencies and so on and so you try to keep the MTIE below 1% of the cycle time. And voila, you're ending up already with a 1 gigabit link with such a high accuracy. Now, if we wanted to take the same mechanism to 100 gigabit, maybe even reduce the cycle times, then we might end up even with as much as 100 times better clock synchronization. So that wouldn't be possible because the clock synchronization can only go to a certain degree. Every time you're making clock synchronization more accurate, you're increasing the cost of the clock synchronization, right? So that's in our opinion, the most important factor. So then we have differences in the link media propagation latency. One good example is the length of the link changes, right? So if you have any type of wires hanging from poles, typically those are on power lines, but in the US, I think almost everything is over the earth copper or fiber lines, and then they actually do hang through a lot more. You see it in summer. So if you go into power networks, they do a humongous lot of calculations. They're seeing 30 to 40% length increasing between the hottest and coldest times, so even through a 24-hour cycle. So that's one example of actual differences in link and media propagation latency. I'm not sure actually. I put all the factors that impact on that do create variations in the right buckets, right? So when we look into processing latencies, right? So we have various different advanced mechanisms: forward error correction, retransmissions. So for example, in DSL, we have 8 millisecond windows. If a packet is lost, that one is recalculated from FEC, would be 8 milliseconds later. Obviously, it's a bad example. That's way too much of a low-speed link to be of interest, but just, the only FEC example that I really understood well. I have never looked into the 100 gigabit FEC that I think they also have there as well. Wi-Fi radio links, I don't think all of them are processing latencies, right? We also got interference, reflections, which I'd rather say are linked media propagation latencies. Then when we get into actual high-speed fabric-based multi-line card forwarders, and I'm not sure if people remember from early days in DETNET when we had these discussions on the basic forwarding plane, right? So there are a lot of variations possible in the processing, and you can argue that, we can shape these out all at the lower layers, and basically just take the worst case latency that we're going to accept and buffer up everything. But this may actually introduce a lot of unnecessary complexity at these lower layers, if instead we can solve this problem in the CQF solution. So that's basically, in our opinion, then also a overall system design simplification by having this shaping effectively happening through the CQF layer. Next slide. Sorry, did I lose you, or I don't see the slide moving?
I turned off my mic. Let me turn it back on. Sorry. What I was going to say is I would suggest that we use the term jitter for where you have different processing latencies, so that the link has both latency and jitter properties. That may help with clarity. Okay. My apologies. Next slide.
Yep. So here is an attempt to visualize the problem and explain why the variations, the jitter in processing, in propagation, do necessitate putting the cycle identifier into the packet in some shape or fashion. So we started with the previous picture, right? So we have cycle 1. Now we're also showing cycle 2. Now, if we look at the bottom here of the picture, we have some cycle I, and we have the variation, and that's the orange part, right? So what effectively happens is when a packet arrives, and we're looking at the arrival time to identify which cycle a packet comes from, we have to add all the variation as kind of attributing to the possible time window in which, for the clock of the receiver, packets are arriving. And when you then paint two different cycles, in this case, cycle 1 and cycle 2, you see that the arrival windows are overlapping, right? And so this overlap of the possible arrival windows of adjacent cycles means that we cannot determine from the arrival time alone which cycle the packet was sent from, right? So let's go to the next slide where we're kind of discussing this in more detail. Right, so we cannot simply guess that, right? The sending cycle and put the packet just into, just one of the cycle buffers will fit. So that completely messes up the admission control, the latency calculation, and creates possible congestion packet drop, right? So we could use the dead time concept, but if you go back to the prior slide, you'll see that this quickly reduces the possible throughput, right? With variations of 50% of the cycle time, the throughput already goes down to 0 in terms of the dead time that we effectively are getting eats up the whole cycle time, right? And with tagging, we never need to reduce the throughput, right? But the higher the variations, the higher the jitter, the more cycles we simply need, right? So, this is another part we still need to put in more detail into the drafts, but I think it was easily visible from the prior things. So if we have less than 50% cycle time, then 3 cycles will suffice. Next slide. So here in summary, right? So we think that CQF has attractive features and potential for large-scale deterministic network deployments. Multi-buffer CQF is straightforward extension from TSN, easy to build POC hardware, cycle-to-cycle mapping configuration based on link propagation latency, and the number of cycles based on variation, right? So then simply we need to eliminate the reception time-based assignment of packets to a cycle buffer. And so instead, we're relying on a packet metadata where we put the cycle ID into the packet header. We're calling, in the case of my draft, we called it tag because, you know, late in the 90s, there was a technology that was called tag switching. Some packet header field which was rewritten in every hop, and magically that actually was later called MPLS. So Stuart basically suggested that we call this then now tech-based CQF, right? So in result, we can support arbitrary links. We can support lower clock sync accuracy, right? So we can go up to MTIE that is larger than the cycle time, and simply calculate how many cycles we then need together with the propagation latency. And of course, we can support higher node propagation latency variations as well in case we do have that. And I think we're especially then also safe if, let's say, the mobile world wants to come and also adopt this, and not only the wired links that we are, I think, currently mostly looking into. Okay, next slide. Okay, so here is kind of a couple of sections which hopefully we can run through fast. So these are repeating what I was, I think, presenting 2 years back, just as I think reminders. Why is low jitter important, and what impact does it have to the overall design complexity? Next slide. So this was some picture to outline that we've always been thinking about 2 types of application requirements, but also mechanisms that we have in the network, right? The in time means that the packet can arrive as fast as possible. So if the network has no other competing traffic, then there is no queuing latency. So TSN ATS is an example of that. C-Score, I think, is claiming to do the same. Still need to sit down on the details. And then, of course, if the network is loaded with the maximum amount of traffic, then you have the maximum bounded latency. And in the on-time case, you have just a very small red window of latency variation, jitter. And so TCQF, CQF, they're all on-time mechanism. And the damper mechanisms as well. So those are the 2 things we're primarily looking into. And so why are we interested in the on-time mechanism? Next slide. So this goes pretty much back to how a lot of distributed applications are written that want to have deterministic networking. And so manufacturing is one example, but if we look into large-scale networks, then it would equally, let's say, remote driving of a car, cloud PLC, and so on. So what we have are control loops where packets are being sent between, let's say, one central entity, often called the PLC in industrial networks, and then many, so we're just showing 2 type of devices. Some of them are only returning data, they're called sensors, and then others are basically doing something, they're called actors. And what you're doing from the central logic is you're sending out packets that are triggering a response. And so the sensors and actors in an on-time service in the industrial world, it's called synchronous network or synchronous traffic. The arrival time of the packet and the immediate triggering of the response that is by itself the timing mechanism. The sensors and the actors, they do not need to have clock synchronization. The central device knows what the latency is, what the guaranteed synchronous latency is to each sender and each actor, so it can calculate when to send the packets, to trigger an action at a particular time, or to get a feedback that is from a sensor that is valid at a particular time. So you are not requiring clock synchronization through the network to all these devices. So if we are now replacing this type of deployment from synchronous networks with the mechanisms like TSN-ATS, which is asynchronous in the network, then we're going back to building more expensive sensors and actors that need to have clock synchronization so that they get these packets that arrive too early, buffering it out so that at the point in time when, you know, the PLC wants to have the actual response, they can start responding, right? And so that means that even if I take out supposedly clock synchronization from the network with something like TSN-ATS, I need to bring it back to the network just to be able to provide clock synchronization to the client devices. And if I look at a lot of networks like, for example, mobile network access rings, every node in that network is connected to edge devices. So I pretty much have clock synchronization back everywhere. So that's why the benefits of TSN-ATS, and we had these type of meetings with people from the industrial world or so, aren't necessarily very popular in these type of application environments. Next slide. So I think I said this all. Next slide. Okay, scalability, next slide. So this is now kind of the outline of how networks with our current per flow, per hop, state-based models like TSN-ATS have to look like, right? So how INSERV RFC 2212, TSN-ATS would look like. And you see on the bottom a multi-hop networks with a service provider notion of the provider edge node connecting to senders and receivers, and then intermediate hops, even if they are, you know, serving for other flows as edge devices, still we need to look at the totality of flows that they're dealing with. And so for every TSN-ATS or, you know, INSERV flow, what we need to do is the controller plane needs to push down for each of these flows a state, and you need to process this state, right? So there's both controller plane, signaling plane, and then execution forwarding plane impact. On the forwarding plane, the biggest issue is the per flow shaper, which was improved with TSN-ATS with an interleaved regulator, but it is still a per flow hardware processing that in large scale wide area networks would need to scale to a large number. And I do have, from a completely different technology, a lot of experience. So we did exactly deploy this in wide area networks with a technology called multicast, not for queuing, but for replication. And customers really hated and still hate the need of having to look on every intermediate router into the behavior of every individual multicast flow TV stream, and which is why, you know, in the IETF for 5 years, we've been working on getting rid of that per hop, per multicast tree state. So very same, you know, thing, different technology, but obviously same, you know, requirements, desires from network operators. Next slide. Right, so the scalability issue, I also showed this slide, right? So it's an n square issue, right? Of course, we're coming in and saying, well, you know, we have aggregation. When we get into the service provider network, we can aggregate all the flows that are behind our sender edge device that go to the same egress edge device, to the same egress PE. But if we have 100 PE devices, then we just have 100 times 99 divided by 2. So we have, you know, 100 square in the order of that many flows. And that's where we need to have shapers for. That's what we have interleaved regulators for. The signaling whenever these are changing, right? So, and if you look at it in TCQF, on each of the intervening routers, we would just need 3 to 5 cycle queues on P1, on P2, right? So totally independent of the number of edge devices, however many queues we need to have in the hardware and need to define mapping tables for. It doesn't depend on the number of edge devices. Next slide. And so that ultimately really brings us to then the desirable DETNET QoS option, right? We, of course, still have the controller plane. We're still doing all the wonderful calculation for every aggregated, unaggregated flow that we want to have through the network. And we still need to talk from the controller plane to the sender, and then also the ingress PE to make sure that, you know, the senders aren't sending too much traffic. But then on every hop, on all the P nodes, when we only have our TCQF cycle queues, we really have what I would call, and I'm happy to hear if David disagrees, what I would call a diffserv only per class QoS, right? So with a TCQF maybe being one diffserv class, of course, needing more than one marking for it, the cycle ID, but that's basically is exactly the same scale discussion, which in the 90s, kind of 30 years, 25 years ago, brought us to go away from inserv to diffserv. And I think that's exactly the same direction, which I think hopefully we're going to get through TCQF or one of the other mechanisms here for large scale networks with the bounded latency and hopefully the tightly bounded jitter. Next slide.
Okay, David says we can split hairs on exactly what words to use to call the concept later. Diffserv has this structural concept already with the notion of multiple drop precedences in a in a group, and this would be applying the concept in a different context.
Yeah, that's a good comparison. Okay, so summary. Metro and larger network operators do not want per flow per hop state on P routers. It's an operational nightmare. It is why segment routing in MPLS, in IPv6, and BEER in multicast were created by the IETF, right? It's about control plane performance, reliability, scale challenges, updates to each P routers. And the DETNET solutions need to support all those stateless forwarding, traffic steering options, right? So we need to have something that works well with these mechanisms and not only ones that require per hop steering setup like RSVP-TE was doing before the whole service provider world moved to segment routing.
Small interrupt, Turles. Could you remind everyone what you mean when you say P router?
So that's provider core router, right? So P and PE. PE is the provider edge router, so it's the first hop into a service provider network, and the P router is then a router internally in the service provider network, and then the packet ultimately arrives at the egress PE router, where it is passed on to the customer again.
Thank you.
So that was in the pictures on the bottom, and yeah, the slides are then readable. Yeah. Right. So, and I think I'm repeating that a little bit as a summary, right? So I was referring to that we did go through the same discussion in the 90s, INSERV, RSC2212, exactly because of the same reasons. But I think the problems today with more hardware, faster hardware, becoming even more important, and also from the multicast experience, it wasn't only kind of looking at thousands of multicast states. It's also the problem which, if we expand the DETNET use cases, or even some of the use cases we have in the DETNET work already, one of the important core things to see is that traditionally, if customers are changing traffic, that doesn't impact the behavior of the service provider routers forwarding and control plane, right? So only when the topology of the network changes does routing change, right? So now it's certainly not 100% true if over longer periods of time the whole traffic patterns of customers are changing, then you do change your traffic engineering accordingly. But that's a very convoluted, complex, well-planned and long process. You cannot have a few customers very quickly creating big changes in the control and forwarding plane of the router in normal unicast. You can do that exactly with multicast because you create a lot of flows, and these flows create state on every P router. And so you have, total new type of attack vectors. And that was what another aspect of what was killing normal multicast and service providers. They wanted not to have these attack vectors. And the same way, if we consider that we don't want to have long provisioned DETNET services where you say, oh, I'm sending a fax to service provider and a week later I'm going to get, my DETNET service class. But you're starting an actual application like an instance of a remote driving, and you want that traffic to immediately have DETNET services with guaranteed latency and low jitter, then you're also talking about what service providers may call auto provisioning, automatically application signaled, and that whole signaling and that admission of resources should only go to the controller plane, and at best to an ingress router on the service provider, or a service provider managed CE, but it shouldn't impact any of the state in the core routers. And only these stateless mechanisms, like what we can get with TCQF, will allow for that. Next slide. Okay, so that gets us to the wonderful short section on packet encapsulations of the cycle identifier. Next slide.
Okay, just a quick reminder that we're separating selection of the queuing and scheduling mechanisms in the nodes from dealing with the data that has to be communicated to make them work, and the packet encapsulation is about how to communicate the data.
Right.
With that, go ahead.
Yeah, next slide. So, of course, I think it's fine when we, architecturally want to separate that. And by the way, there is this, on the last slide, the question of what should we put into which draft. I think what I have a hard time in separating out just architecturally is that different encapsulation options, of course, have different pro and cons, and different mechanisms have different pro and cons with respect to different encapsulations. So one of the biggest benefits for short-term adoption of any mechanism is that if we can fit it into existing packet header tags that we can use, that's, I think, a deployment benefit. And because we only need a very few different values to carry the cycle ID, which 3 or 4 would be perfectly fine for a lot of initial deployments. It can fit, for example, in the MPLS traffic class field, where we arguably could have 4 values. In DSCP, we can have up to 16 private DSCP, so that will give us, I think, all the cycle IDs we would ever want. So that's an interaction. I think it would be good to be able to somehow highlight that as possible value proposition compared to other mechanisms. Even mechanisms I would prefer longer term, but which would require a lot more header work. But even in TCQF, obviously, when we have the discussion, how do we do extension headers? Then obviously the question is, are we going to have extension headers differently for each queuing mechanism, and then also for the other DETNET aspects? I, for example, would be a fan of having a single DETNET extension header, at least for IP, right? So the deterministic IP header or something like that. So just to that extent, one of the 2 drafts that we've written, next slide, please, is proposing as a starting point.
Okay, let me quick make one comment on this slide. There is, believe it or not, a severe understatement on this slide. Right about in the middle of the slide towards the right, it says TC is quite limited. That's being very polite. There's a lot of stuff that tries to go into TC.
Okay.
If anything, you have a bigger problem with TC than you have with DSCP.
Right. I'd certainly love to find some, hallway time to be educated on that, because you're probably because all the
I would
MPLS
suggest
experts.
I might
Yep.
suggest you talk with you. I might suggest you talk with Stuart Bryant, who is very familiar with everything that that wants to land in TC and what happens out there.
Well, actually, I think that was the one pieces where I think Stuart could remember a lot of drafts, but I think the problem was a little bit the difference between drafts and that what was deployed in networks. And so the deployment memories that we have was that there was really not that much adoption of different TC values in networks. So, and that may be wrong. So, because that might have come a lot later. So that's why certainly more input. Yeah, I talked with Stuart a lot about that when we started the draft. Okay, so and when it comes, so the proposal, of course, with IP, being well underrepresented compared to MPLS in the forwarding plane natively, there would certainly become a discussion with the 6-man working group. So the draft specifies some possible options. So with the destination option header and the what was the other option header called? I'm always the hop-by-hop header. So obviously we know there is a lot of ongoing work already in 6-man. So that's rightfully something which I think we should start talking about 6-man, how they would like to see, this being discussed with them. And so the header here, very simple, right? So typical overhead of an IPv6 extension header, cycle ID, and then also proposal for starting extensions. I think we may want to think about adding the fields that we wanted to have for pre-auth to that, right? So there was so we'll leave it in here right now in our drafts, and then see how that goes in the discussion. Next slide.
Okay, quick note of feature in this slide. There's a nasty acronym collision on DOH and IETF. You probably ought not to be using that acronym here.
Which DOH do we have?
DNS over HTTP.
Oh, yeah, I was already.
Yeah, just a warning, particularly if we for discussion outside of this working group, we have that acronym has a collision problem.
That's a good question. If what 6-man says about that, right? Because they were a lot earlier than the DNS people. Next slide.
Okay, you should be looking at specification outline.
Yep. Right, and so I think that's a general. Yeah. Next slide. Yeah. So and I'm not going to show any of the slides with the details of the specification. We very much overhauled by integrating in the next version the second draft, the over motivation background. So this from CQF to TCQF to understand those details. Then we already got the section how it fits the DETNET architecture, which is also trying to bring in that type of aggregated behavior, kind of like more like DETNET. And then of course the specification of the forwarding plane with a per hop configuration model, where basically for every incoming interface there is a cycle mapping of the received cycle to the outgoing cycle based on population by the controller, and then the per hop packet processing specification. So how to basically send the packet to the output queue, cycle ID, termination, textual and pseudocode. I'm coming from the multicast side, so we've kind of developed a preference there with pseudocode. Love to hear if people like that. The ingress node behavior, where for each individual flow, we need to determine, how to put the packets into the cycle buffers. Obviously, we're trying to keep this at a minimum. I think that's not necessarily, in our opinion, even part of the basic specification. But for the systematic stuff, I think it's good. You could equally use something like, the TAS mechanism on the first hop router from TSN for that. And then Section 5 per encapsulation specification, so the details of what is different in the different forwarding planes. Mostly it is about, I think, encapsulation, but I also thought that the kind of where stuff is carried, what's the semantic in MPLS between the service and the transport label. So I think that's not necessarily only encapsulation. But yeah, next slide. Yeah, and then the consideration chapter, right? So high-speed optimizations, how implementation can be made easier, the computation of the cycle mapping at the controller by taking link latencies and then different clock offsets into account. I'm not sure what other issues for the controller plane are important for us to specify. I think most of the calculation is really very simple. Support for TCQF across links with different bandwidth. I think that's an interesting aspect that may not be obvious that it's very simple for everybody because it's also just a controller plane issue. And then I think general controller plane considerations, there was feedback in terms of, do we need a centralized controller? Can it work decentralized? Yeah, we can also use the same decentralized mechanism that we've, for the controller plane that we've done in the past for decentralized CSPF calculation with RSVPTE, but of course it will run in the same issues when we get into the high utilization space. So I think there are some basic things, and I'm not sure kind of how we're actually going at some point in time to talk about that with T's. Yeah, so I think in general it would maybe one of the subjects for the team overall is how do we progress with these drafts in terms of so that they're mutually more common and easier to absorb for the other draft owners. So certainly opinions very much welcome. What we should do here for the structure and the content of the draft. And I think that's it. The next slide. Nope, that's it.
Okay.
Thank you very much.
All right. Any comments or questions? Xiaofu, go ahead. And let me just flip back here. If I need to go to a particular slide, please tell me what slide I ought to go to. Xiaofu, if you're speaking, we can't hear you. All right, Xiaofu unfortunately is losing his battle with the mute again. That's unfortunate. Hopefully he can overcome it. We can have a discussion. Any other questions or comments?
I think so Kieran had one question about the cycle sizes, whether they can be changed or configurable. And I'm trying to remember if I wrote something there. I think there is a requirement for one particular cycle time to be supported. I think that's very much for us to specify in the spec what requirements we want to have against interoperability, right? So that's I think fairly wide open how broad or how limited. I think we definitely need some mandatory to implement set of parameters. I did specify a must for 3 cycles, probably should be a must for 4 cycle operation, and then some mandatory cycle times that we would agree on. I think that's the minimum, and anything more that the IETF working group feels appropriate should go in the draft.
And I think it's probably worth noting at this point that all of the nodes involved have to use the same cycle time.
So my best understanding is that so that's that I wrote in the controller spec that that's not necessarily true, but you need to be able to do the mapping, right? So if you have different speeds, if on certain links you don't have the full capacity of the link that you're offering, right? You obviously can have different cycle times. I'm trying to remember if I had a more succinct summarization of the conditions so that you can have different cycle times. Let me take that as a note here to review myself from that section, because it's been a long time that I worked on that section.
Yeah, I mean, at a minimum, I think all of those have to agree on what the duration of a single cycle is. Otherwise, I think you have an opportunity for confusion. Kieran, go ahead.
Yeah, so Torles, does that mean if I have 1 gig link over a 10 Gbps network, everything will reduce to 1 Gbps network?
No, certainly not. Obviously, the aggregate of traffic that you can pass end to end across a 1 gigabit link will not magically be more than 1 gigabit. But obviously, on the next 10 gigabit hop, the same cycle can already multiplex packets coming in from other paths, right? So that can again, be a lot more than 1 gigabit.
Okay, thanks.
Let me see, were there other?
Don't see anybody else, so I'll drop in a question. So, Turles, in listening to you, it occurs to me that, but by comparison to past sessions, I heard the word multicast a lot more this time. Do you believe the scalability draft adequately covers multicast in addition to unicast? This is the requirements draft.
Yeah. I probably not. Everybody forgets about it, and I'm now joining those ranks. So.
All right, I think
No, I
know
haven't
where to
even thought
find
about.
it.
Yeah.
Okay.
I was only using multicast as a comparison of actual deployed experience with per customer, per application, traffic state in networks, right? And that we made miserable experiences with that. But I think
Right.
yours is a completely different point, and yeah, I'll have to go back to the requirements draft and talk it and see the multicast part as well.
Yeah, I'd suggest you find the cycles to look at the requirements draft and ensure that it does an adequate job of covering multicast, please.
Yeah. Especially because it's the funny part is that in TSN you don't hear it being talked about a lot, but then it actually is supported in all the places. And when I talk with people in the car industry and so on, they're actually also using it. So it certainly is not to be ignored. So any opinions that people have about structure of the document or that type of thing that may not be applicable only to CQF? I'd certainly love to hear what people think about how we can improve the drafts.
Okay. Any other comments or questions on what Turles presented or anything in anything that's in scope for this meeting? Okay, so I think we're done for now. Would very much like to see someone, hint, hint, take on evaluation of the CQF mechanism against the current state of the requirements draft. This is not so much about is CQF unmodified useful, but rather shaking out whether we have a good set of requirements in the requirements draft that is useful for evaluation of these mechanisms. Janos, anything you want to say before we wrap up here? He must be tied up with IEEE stuff this week. All right, any closing words from anyone? Kieran?
Just for a clarification, so when you talk about evaluating with TSN, it is only for the cyclic related stuff, not for the asynchronous part of the queuing.
I think anyone who's willing to take a shot at evaluating any of the TSN mechanisms against the scaling requirements draft would be greatly appreciated. I'm just looking for, let's take one of the TSN mechanisms, which is not sort of up for debate, whatever on whether we adopt it here, and use it to do an initial test on usability of the requirements draft. So if you'd like to do a different mechanism, that's fine. I've just simply been suggesting CQF because this is the second session in a row that we've been looking at extensions to CQF.
Okay,
If
so
you'd like to take another one, please go for it.
Mhm. So my understanding is requirements draft is slightly broader, right? It is addressing large scale issues and not only specific to the queuing aspects. So will it clutter the document if we try to bring in that perspective?
I'm not sure I understand the question. The requirements draft ultimately is going to wind up providing us some guidance on the data and the encapsulation, but there's quite a bit in the requirements draft that can be used to evaluate the queuing and the queuing and scheduling.
Kieran, so the ask is for just some freely written text that can be reviewed in whatever shape or form, discussing how well a mechanism, pick your choice. CQF is
Right.
popular right now because we talked for 2 weeks about it, right? So how such a mechanism existing from TSN does or does not meet the requirements. And I think the answers to the requirements of the review cannot only include meet, does not meet, and why, but also, okay, this requirement does not, account against
and
the basic mechanism itself, but is encapsulation specific, for example, or something
Yeah,
like
I
that, right?
was
So review.
Yeah, so only subset of the requirements in the document would map to queuing and scheduling. And when we present a requirement, we do not say that this belongs to, this can be satisfied through asynchronous queuing mechanisms or synchronous queuing mechanisms. So, or should we put potential solution how those requirements could have been fulfilled in TSN? And
the
then some
request
gap.
is to take TSN, to take one or more TSN mechanisms as they exist and do a brief run through the requirements draft, resulting in a sentence per section requirements draft of whether it meets, partially meets, or does not meet the requirement and why. speculations on extensions for TSN are not helpful. The goal is to take something that's known and understood and use that to test the use of the requirements draft. Is
Got
that
it.
making sense?
Yeah, it does. I think we have to
Okay.
take one example, run through it, and see if it satisfies what we are trying to achieve from the requirements document.
And we do only want to improve our requirements draft. We don't want to improve TSN mechanisms for TSN.
Right. Right. I mean,
That's a
the
challenge.
goal is, right, as Troy said, the goal is to improve our requirements draft so that when we use it to evaluate the new proposals, we have some confidence in its use. Okay. Any other comments or questions on anything?
Well, thank you so much for running this again.
All right. I do believe we're done. Thank you, everybody, for taking the time to attend and participate.
just for test.